My great pleasure. It is my great pleasure to give the talk here, and I would also like to thank the organizers for organizing this wonderful event. But due to the jet lag, I did not really listen to much talks. So for this talk, I apologize that I delayed part of the talk itself, or otherwise the contents will be too much. But nevertheless, I will talk about the non-equilibrium time evolution process in Ising chain with periodically driven transverse field, mainly about its adiabatic time evolution process, where I will introduce you a quantity named the quantum geometric potential and tell you how to use it to characterize the adiabatic time evolution and the many-body non-tunnel process for quantum many-body system. So the contents will be given by, first of all, I will introduce the model, and then I will talk about how to solve the barrier conduction matrix element and its property in the integrable quantum field theory. And then I will show you a new quantity Loschmidt echo spectral entropy to characterize the many non-tunneling process. And finally, I will give a summary. So the motivation of this study starts from the fast developing quantum simulators given by the Lindbergh quantum area. So locally, you will have the Lindbergh atom, which creates you some two-level systems starting from the ground state to the Lindbergh state. And you can actually do a map, a correspondence between the spin states and the Lindbergh states to create some effective spin model. Although the Lindbergh quantum simulator could simulate lots of different types of quantum systems, but essentially there will be some background Hamiltonian of the system itself. So if you have a bunch of Lindbergh atoms, then you will have the effective Hamiltonian as I showing here. And after making this correspondence between the Lindbergh states to the spin state, to the two-level spin state, you will find that you can rewrite this effective Lindbergh Hamiltonian into some spin Hamiltonian with Ising interaction and also a rotating transverse field. So we can make some further assumptions to this effective Hamiltonian, just like we can make this phase phi t equals to some omega t, which is linearly in time, and we can ignore some Lagrange interactions in the system, such that we will have a minimal effective Hamiltonian of this system. The original Hamiltonian of the Lindbergh quantum simulator is given by antiferromagnetic coupling of the Ising spin, but now I just assume that this is a ferromagnetic coupling, such that this question will be minimally simple. And the Hamiltonian itself is composed of the Ising spin interaction with the longitudinal field, where there will be a static longitudinal field along the z direction and also a rotating transverse field in the xy direction. We set both the rotating frequency omega 0 and also the longitudinal field strength Hz goes to 0 plus. And the Ising coupling, I set it as J equals to 1, serves as the energy unit of the system. So there might be some other simple limit for solving this system, but at least for myself, this limit is relatively simple to solve this question. So we could first see some basic properties of this model. That if I set the time equals to time t equals to 0, this is just a critical transverse field quantum Ising chain with a longitudinal field perturbation, whereas its HD is goes to 0. Then if I set the initial state psi 0 equals to the ground state of this initial Hamiltonian, this initial Hamiltonian, if we take the scaling limit, you will find that this is given by a integrable quantum field theory, which is known as the quantum yet integral model. I will give a very simple introduction to the integrable quantum field theory, which is the quantum yet integral model. The Hamiltonian is given by the critical transverse field plus the weak longitudinal field. So if you take the scaling limit, you will find that this model is exactly given by the minimal mode, the central charge 1/2 minimal conformal field theory perturbed by its most relevant uh, operator, which is the spin density operator. And Alexander Zablotchkov, in the last century, he proved that this model actually enjoys integrability, given by that there will be infinite many local conserved quantities commuting with the Hamiltonian. And by employing the so-called asymmetric bootstrap method, you will find that this model contains 8 different types of quasi-particle excitation. where the mass ratio of this at different types of quantum particles, they shares they serve as the simple rules of the Lie algebra, and there will be a one-to-one correspondence between the diagram of the Lie algebra to the mass ratio of the integrable quantum field theory. So this is why this model is called quantum Lie integral model. And once you know the strength of the neutrino field, you can actually solve the mass of the lightest particle M1. This is given by some similar techniques of this model dynamic based on that. And once you know the mass ratio of the specific mass of M1, you will know all the mass inside this model. The essential physical picture of this model is given by the Z2 spin confinement. Since originally, if without this Lagrangian field, you will have the free propagating domain wall in the transverse field Ising chain. But with this Lagrangian field, you will find that every time the spin flip will cost a certain amount of energy, which is the similar mechanism as the confinement in the QCD system. But along this very special line, this low energy quantum field theory is proved to be integrable. And once we know that this model is integrable, we can use some techniques given by the quantum integrable field theory, just like the four-factor bootstrap, to solve the matrix element of the system, such that we will know the excitations and the correlation functions of this integrable field theory. And based on these techniques, I don't want to introduce them, but I will use these techniques to solve some questions that we concern about. So let's move on to see some more details about this model itself. So once the time once the time is not equal to zero, which means that I trigger this time evolution process, we can find that by applying this unitary transformation, we can actually rewrite the time evolution process of the wave function given by this effective Hamiltonian quench to the initial wave function plus this times this unitary transformation itself. And the effective Hamiltonian is given by that the longitudinal field here from Hz is modified from Hz to Hz minus omega 0 over 2j, which is another, if Hz is not equals to omega 0 over 2, then this is just another different quantum yet integrable field theory in the low energy, in the IR limit, the low energy region. And we can also care about the instantaneous eigenstate of the system itself. So actually, by a very simple proof, you can see that the energy of the system is actually does not evolve with time. And we can exactly write down the instantaneous eigenstate given by the unitary transformation to the initial state of the system plus one additional a little bit random U1 global phase of the system. So we call the wave function that is according to the time evolution process from the Schrödinger equation the so-called dynamical orbit, and call the instantaneous eigenstates of the instantaneous Hamiltonian as the so-called adiabatic orbit. Then there will be a question that you can generally ask here, that what is the property of the time evolution process for the dynamic orbit in terms of the effective, in terms of the instantaneous eigenstate, which is the adiabatic orbit. We can think about some limit of the Hamiltonian itself, just like we can first make the omega naught, omega 0 goes to 0, and we can make the Hz much larger than the omega 0 over 2, which means that we can ignore this term. And we will find that in this case, the time evolution itself does not change anything, but just with one additional phase to the initial wave function. So this actually means that if the Hz is much larger than the omega 0 over 2, the time evolved wave function will stay around the ground states, or say the initial states of the initial Hamiltonian. And once if Hz is compatible with omega 0 over 2, there will be some tunneling process from the ground states, or say from the initial states, towards the high excited states of the instantaneous Hamiltonian. So then there will be a competition between the adiabatic time evolution process to the non-Lorentzian tunneling process, which is a many-body case. So now we want to study this post-body adiabatic time evolution process inside this many-body model. So I will first give an introduction to the adiabatic time evolution. So the adiabatic time evolution is given by that for a time-dependent Hamiltonian starting from eigenstates of the initial Hamiltonian. Then we can drive the system with the Schrödinger equation to consider this time evolution process. This time evolution, if this time evolution process approximately keep the time evolved wave function in the corresponding instantaneous eigenstates of the instantaneous Hamiltonian, then we call this time evolution process is a adiabatic time evolution process. More specifically, we can make some definition here. So here, this definition is just follow up the original definition just now I introduced the model. So we can set this. We can introduce this adiabatic orbit, which is given by the instantaneous eigenstates of the instantaneous Hamiltonian, and then we can also introduce the dynamic evolution orbit. We can even modify this dynamic orbit a little bit to make this eigenstates to make this time evolved wave function being UY invariant. So this is called the UY invariant adiabatic orbit. You can prove that with this additional phase, then this whole Hamiltonian will be invariant under any types of global UY transformation. And here the gamma NN is the so-called barrier connection matrix element according to the time evolution process. So we can make the adiabatic time evolution, the definition of the adiabatic time evolution more specific. That is, if we consider the Hamiltonian being n-level time-dependent Hamiltonian, then we can expand the time-evolved Hamilton wave function, which is a dynamical orbit, with a UY invariant adiabatic orbit. So we can write out this expression of the wave function, and then the adiabatic time evolution process exactly means that the corresponding coefficients of the nth energy level CNT, the absolute value is equals to 1. So this is the more concrete definition for the adiabatic time evolution process. And then there's coming a question that how can we find the adiabatic condition to make the time evolution process as a adiabatic time evolution process? A very naive idea is that we can make the energy gap as bigger as possible. So we can start from some ground state of the initial Hamiltonian and make the gap between the ground state to the excited state very large. And then we can trigger the adiabatic time evolution set with a very low frequency, such that it cannot overcome the gap. Then it will forever remain around this ground state. This is a very naive idea about find some adiabatic condition. But here actually we can prove some more concrete adiabatic condition to this to a very general n-level Hamiltonian, time-dependent Hamiltonian. That is, we can introduce the quantity which is the effective energy gap between the jth eigenstate to the nth instantaneous eigenstate. So here the eigenstates are all the instantaneous eigenstates. And this effective energy gap is given by the difference of the effective of the instantaneous energy levels of the instantaneous Hamiltonian together with this so-called quantum geometric potential. So here the quantum geometric potential is given by the difference of two diagonal barrier connection matrix elements of the instantaneous eigenstates. And it is proved that in this paper, there is a quite detailed proof in this paper that once we have this effective energy gap together with the non-diagonal barrier connection matrix element satisfy this condition, then this delta will be served as a small quantity, as an error to the adiabatic time evolution. Namely, the absolute value of Cn larger than 1 minus delta is equivalent as the delta and the non-diagonal barrier connection matrix element and also the effective energy gap satisfy the condition of the left-hand side. It might not be a very good upper bound, but this is an exact upper bound. Since you can see that if we really consider some quantum mathematics system, then the numbers of the energy level, capital N, is grows up with some exponential to the local degree of freedom for this quantum mathematics system. So such that the application of these quantities of these conditions will be very difficult to some quantum mathematics system. But nevertheless, we can first see some effects of this quantum geometric potential and also the effective energy gap to some field level quantum systems. So we can first consider some two-dimensional quantum system where the degree of the Hilbert space is just a two. So we can propose a very general two-level quantum system given by the combination of the polymetrics and its local spin rotation. And we can find the two adiabatic orbits given by the two eigenstates of the time-dependent Hamiltonian, and then we can solve the quantum geometric potential of this system itself. You will find that the quantum geometric potential between the two energy levels is exactly the geodesic curvature of the corresponding two-dimensional quantum system. And once if you have the quantum geometric potential itself goes to zero, this is exactly the geodesic size in this two-dimensional Hilbert space. We can even consider a more general two-dimensional quantum system given by the Hamiltonian as this one. And since this is just a two-dimensional quantum system, we can exactly solve the tunneling probability between the ground state and the first excited state, which is given by this formalism. And we will find that once the delta plus FR plus minus over 2 equals to 0, then we will exactly have the tunneling probability goes to 1, which is the perfect Laurent tunneling process. And if you then solve the effective energy gap of this system, you will find that this delta plus Fr plus minus over 2 is exactly the effective energy gap of the two-dimensional quantum system. So this suggests us that this suggests us two things. First of all, we can consider about the question that if we can generalize this adiabatic time evolution condition to a more general quantum many-body system with much more energy gaps of the much more energy levels of the system. And the second point is that if it's possible to really apply this adiabatic condition to such system, that is, since the capital N will be grow up exponentially to the system size. But however, if we can find the zeros of the effective energy gap, then we can exactly claim that at the zeros of the effective energy gap, there must be some perfect tunneling process happening in this system. So we do not try to find the specific adiabatic conditions of the system self. Instead, we try to find in which parameter space the system will enjoy a exact perfect many-body Laurent tunneling process. So this requires to solve both the quantum geometric potential and the effective energy gap for the quantum many-body system. So first of all, we can try to solve the quantum geometric potential for the quantum many-body system, and this requires us to solve the sorry. This requires us to solve the barrier connection matrix element of a general quantum many-body system. And that will be a little bit difficult if you do it too general. So we can first start from some integrable systems, and then let's see if that we can, if in that case we can generate from the integrable case we can generate this calculation towards a more general quantum many-body system. So we consider the integrable quantum field theory, which is quantized on a finite system L, but this L is large enough such that we do not consider the finite scaling effects of the system. The initial state is given by n-particle eigenstates of such integrable quantum field theory, and we consider that there will be a temporal unitary transformation which connects the instantaneous eigenstates of the t time to from the initial state we consider. So we can generally write down this time evolution. This we can generally write down this unitary operators given by this effective adiabatic Hamiltonian, which is given by the summation of integration for the local operators. In this case, we can directly solve the barrier connection matrix element from the formalism itself, since the initial wave function is time independent. So this is equivalent to that we solve the time derivative to the unitary transformation, such that we can obtain this matrix element. And on the finite size system, the matrix element could be solved exactly by using the form factor framework, which is built up by some Hungarian physicists like Balázs and Gabor-Takács. So in that case, we can solve the normalized barrier connection matrix element for the non-diagonal matrix, for the non-diagonal part and also the diagonal part. There will be some additional density of states shown as a Jacobian in the denominator. And if we recall the property of the Jacobi, which reflects the density of states for the many particle eigenstates, we will find that the matrix element for the barrier connection matrix element for the multi-particle sets will only have the contribution from up to two particle matrix elements. So in this case, we can provide this theorem. That is, if we have the time evolution process effective adiabatic Hamiltonian follows in this form, then we can claim that in the thermodynamic limit, the corresponding barrier connection matrix element will only be analytically obtained from the excitation up to two particles. Actually, this is exactly because of that. In the finite system, if we define the quantum states in a normalized sense, then the many particle eigenstates will have the degree of freedom to the L to n power according to the number of the particles, such that if you solve the matrix element of such many particle states, there will be naturally some density of states shown as a Jacobian appearing in this corresponding matrix element of the operators. So this conclusion is not only applicable to the integrable quantum field theory, but also applicable to some lattice systems that can be described by the quantum-particle excitations. Actually, you can check the transverse field quantum Ising chain. The matrix element of both the sigma x operator and the sigma z operator can be analytically obtained by using the Jordan-Wheeler transformation and also the Majorana Fermi representation. And you will find that there will be some prefactors showing exactly as the L2 minus n plus m power over 2. And in that case, you can directly read out that the barrier connection matrix element will be contributed at least at most to the two-particle process. And this is the conclusion we obtained from the quantum geometrical potential. We can actually identify the quantum geometrical potential for the system we consider in the very beginning, which is the quantum yet integral model. So we can solve any two different eigenstates, multi-particle eigenstates, the quantum geometrical potential of this quantum yet integral model. And this is exactly solved by using this form factor theory. And just with a little bit more algebra, you will find that it is directly given by the difference of the many-particle mass of the total mass of the many-particle states. And we can evaluate and identify these results by using some other numerical method from the perturbed conformal field theory, just like the truncated conformal space approach. You will find that the region that the IR limit could be applied with the quantum yet integral model. The theoretical results from the field theory itself is totally matching with the truncated conformal space approach. We can even solve the effective energy gap, which is given by the difference from the instantaneous energy gap together with this quantum geometrical potential. So after you solve this delta Nm, you will find some very interesting conclusion. So the first of all is that if we set one of the quantum states being the many particle states of the many particle eigenstates of the quantum yet integral model, and the other eigenstate being the vacuum of the quantum yet integral model, then the zeros of the effective energy gap between these two sets actually shares the same 0 point. And this same 0 point, you can solve this zero given by the ratio between omega 0 and HAD. You will find that this ratio kappa is exactly equals to 8/15, which is somehow you can say this is the magic number of the quantum yet integral model. Since in this field theory, you will find that the mass ratio, the mass of the particles, which is a scale of the energy, is proportional to the h to the 8 over 50 power, where h is the longitudinal field. So somehow this is more or less a magic number of this quantum field theory itself. And we can also consider some, and this result is okay independent with the particle type itself. And we can also solve some effective energy gap between the two particle eigenstate to the vacuum itself. You'll find that this magic number kappa equals to 8 over 15, then serves as an upper bound of the zeros of the effective energy gap. And once the total momentum of this two ET particle states become larger, then this upper bound will decrease to until the kappa equals to 0. We can even solve any two different eigenstates of the quantum ET integrable model to obtain the zeros of the effective energy gap. So then in this time, then these zeros will be quite random, depending on the choice of two different states. But I have to claim that if you want to make the ratio kappa larger than 8 over 15, you'll find that the density of such states is much smaller than the density of the usual quantum states that have the kappa smaller than 8 over 15. So we can actually apply this result, the effective energy gap, to detect the many-body Landau-Zeno autonomy process of this model itself. So let me remind you some basic conditions that we have already introduced in the very beginning. So we have this exact adiabatic condition to characterize if this model itself, the time evolution process, is adiabatically time evolving, or there's some many-body Landau-Zeno autonomy process. But for a real quantum many-body system, detect the adiabatic condition itself is very difficult. So we do not do this step exactly. Instead, we try to find the zeros of the adiabatic condition to characterize in which point there is many-body Landau-Zeno autonomy process happening for the quantum many-body system. And
Sorry, I think you only have 2 minutes
okay, so
left.
I will go quickly through, from this way. So we can solve the Loschmidt echo of this time evolution process, where the Loschmidt echo is between the time evolving wave function to the instantaneous eigenstates of the instantaneous ground states, and you will find that the unitary transformation will be cancelled in this Loschmidt echo matrix element, and there will be effectively just effective Hamiltonian quench to the initial state, and then consider the overlap to this quench process. So to detect the many-body Landau-Zeno autonomy process, it is equivalent to detect that how many eigenstates will have the overlap to the time evolved wave function. In this case, we can introduce the spectrum of the Loschmidt echo. So if we do a Fourier transformation to the time-dependent Loschmidt echo, then we will obtain the corresponding spectral weights with a series of delta functions, where once the spectral weight is not equal to 0, then there will be a delta function peak in the frequency region to show that there will be some contributions between the initial wave function to the eigenstates of the instantaneous Hamiltonian. So then the task changed from detecting the many-body Landau-Zeno autonomy process to count how many delta functions is existing in this Loschmidt echo spectrum. So we can introduce the in Loschmidt echo spectral entropy that we only calculate the PM log PM, the summation of this PM log PM. Since this quantity have many very good quantities, just like very good properties, just like the summation of the PM is naturally normalized. And also, if we have only one peak contribution in the Loschmidt spectrum, then this Loschmidt echo spectral entropy will just be given by 0. And if we have many, much more peaks in this Loschmidt echo spectrum, just like if all the eigenstates will have a contribution on the initial states, then this number of these peaks will be exponentially large, and this logarithmic will extract out exponential to the system size, such that we will have a linearly behavior distributed echo spectral entropy of the system. So this quantity could be used to detect the strength of the many-body nano tunneling process. Then we can apply this idea to our model. So here I ignore this, I skip these technical details for calculating this distributed echo spectral entropy, but I can show you some final results. That is, when the kappa is much than zero, which is corresponding to that the longitudinal field is much larger than the omega 0 over 2, you will find that the distributed echo spectral entropy will be very small towards 0. And this is also satisfy our predictions at the very beginning. Since if H is much larger than omega 0 over 2, then you can just consider that this longitudinal field, this transverse field is not rotating in the XY plane, and this is just a usual time evolution process. And once if the HZ is compatible with omega 0 over 2, you will find that the distributed echo spectral entropy will grow up in a very fast scenario. So you'll find that nearby the critical point, which is kappa equals to 1, there will be some hyperscaling behavior of the distributed spectral entropy. And also, exactly at this critical point, this will be linearly grew up for this quantity, which is suggesting that there will be exponentially much more eigenstates contributes to the initial states during the time evolution process, which is also satisfying our predictions for the quantity itself. And for the what's below the upper bound of kappa equals to 8 over 15, there will be much more very strange behaviors for this quantity. But due to the limit of the computational power, we did not really detect in very detail for this data. And finally, I just give a summary, which is a take-home message for you. So the first point is that the quantum ES physics emerges from rotating critical transverse field in Xi And the second is that the adiabatic time evolution process can be characterized by the effective energy gap contributed from the quantum geometrical potential and also the instantaneous energy gap. So this is the end of my talk. Finally, I would like to acknowledge my PhD supervisor, my two collaborators. One is my PhD
Any?
supervisor, another one is my academic junior, both from Shanghai Jiao Tong University. And thank you very much.
Any?
Thank you, Dr. Wang. Uh, I think we can have time for a short question, and maybe let's the remaining talk of today to be postponed for 5 minutes. Does anyone have any question? If not, I have a short question, a naive one. So, you mentioned about the tunneling probability at the relatively before the middle of the section 2. And
This one.
then yeah, it says perfect tunneling happens at the delta equals 0. What does perfect tunneling mean?
So so you can see that there is a factor inside this exponential, the delta plus f r plus minus over 2. If this one becomes 0, then it means that you will have some exponential to 0, which means that the tunneling probability equals to 1. So there must be some tunneling happening during the time evolution process. So this is what we call as a perfect tunneling.
Okay. Thank you. So let's thank